In this video, we're going to look at Chapter 8, Section B on quantitative data, which is also known as numerical data. Now remember from Section A that a quantitative variable is a variable that has a numerical value. Remember also that there are two types of quantitative variables. The first is discrete variable, and these numbers are usually generated from counting. So again, an example would be the number of marbles in a bag. I can count the number of marbles in a bag, and I can't have half a marble or a quarter of a marble. I only have whole numbers or integers. So a discrete variable is one that is often derived from counting. The second type of quantitative variable, remember, is a continuous variable. And this is often found by measuring the data. And again, if I want to look at the weight of something, like the weight of pumpkins that have been harvested, there's an infinite number of weights that could happen or occur. And I can use decimals here. I could have 32.5 kilograms as a weight, or 32.7. There's an infinite range, and so there's a continuous range. Next, we're going to look at several ways that we can organize and visually display discrete data. The first method that we're going to use to organize and visually display discrete data is the tally frequency table. Let's take a look at some data that's found in the opening problem of Chapter 8 on page 170 in your textbook. This data represents the number of pumpkins that were grown in a patch without fertilizer. And this is discrete data because we're counting the number of pumpkins. And we can't have half a pumpkin or a quarter of a pumpkin. In the tally frequency table, we're going to look at how many times each number occurs. So let's start with number 3, which is the lowest number. And we can see that the number 3 occurs twice. That means there were 2 patches where 3 pumpkins were grown without fertilizer. Each time I see a 3, I'm going to use a little tick mark to count off that occurrence. So because there were 2 3s, I'm going to use 2 tick marks. And the frequency of that number of pumpkins occurring is 2, and simply the number of tick marks. Okay, if I look at the number 4, I see that it occurs 4 times. Therefore, I'm going to use 4 tick marks, and again the frequency is 4. If I look at the number 5, I see that it occurs 3 times. And I can do this for all of the data in the table. And if I do that and organize it in a table, I should get something that looks like this. Notice I have the discrete variable on the left, which in this case is the number of pumpkins per plant. The middle column represents is my tally, or the number of tick marks per occurrence of each of these values. And on the right is just the numerical value of the number of tick marks. And that's my frequency. The second method we're going to look at to organize and visualize our discrete data is called a column graph. Let's again take a look at the data, the pumpkin data from the opening problem of Chapter 8. This time, instead of using the tally frequency table, we're going to take the frequency data and put it into a column graph that looks like this. Notice that we have the independent variable on the horizontal axis, and in this case it's the number of pumpkins per plant, and on the dependent axis, or the y-axis, I have the dependent variable, which is frequency, or the number of times that each of these values occurs. We can see that this data lines up closely or exactly to our tally frequency table. We know that there are 3 pumpkins per plant occurs twice from the data, right? The number 3 occurs twice. And so for that value, we see that the column corresponds to the number 2 on the frequency axis of the chart. And that's true for all the different numbers of pumpkins per plant. From this graph, I can quickly determine what the minimum number of pumpkins per plant is and the maximum. And with a little extra work, by adding up the values here, so 2, 4, 3, 7, 11, 8, and 5, I can determine how many total data points I have, which is 40. Knowing that number, I can quickly determine the percentage for each number of pumpkins per plant from our column graph. For example, if I want to know the percentage of plants that produced 8 pumpkins, I can take the number of occurrences of 8 pumpkins, which happens to be 8, and divide it by the total number, which is 40, and get a percentage, which is 20%. And this is the column graph. The last method that we're going to look at to organize and visualize our data is the dot plot. Now the dot plot is very similar to the column graph with a few exceptions. Notice that the dot plot looks a lot like the column graph in that I have columns for each occurrence of the variable, which again in this case is the number of pumpkins per plant. But instead of listing the frequencies on the y-axis, I use dots to represent the frequency. So again, we know that there were 2 plants that produced 3 pumpkins each. And so down here, I represent that with 2 dots. This is sort of a combination of the tally frequency table and the column graph. Likewise, I know that there are 8 plants that produced 8 pumpkins each. And so I have 8 dots in that column. I can use very similar methods to determine percentages of particular sets of this data. For example, if I wanted to know how many plants produced 5 or less pumpkins, I could add up the number of dots, which in this case is 2 plus 4 plus 3, or 9, and divide by the total number of dots, which we know is 40 from the previous column graph, and figure out the percentage, which is 22.5%. In both visualizations, it's very easy for us to figure out which number has the most occurrences. And that's because they're the tallest columns. So here and here. We call this the mode. And the mode is defined as being the most frequently occurring data value, which in this case is 7. Now, in a lot of cases that are naturally occurring, when we have our column graphs and we find the mode, which again is the largest value, or not the largest value, but the value that has the largest number of occurrences, and we draw a curve on top of those columns. This is known as a bell curve. We see that it's fairly symmetrical. In other words, on either side of the mode, the curve looks pretty similar, or symmetrical, right? The mode can be considered the mirror, and on either side we have mirror images. And this is known as a symmetrical data set, or a symmetrical distribution. And this occurs shockingly very often in natural data sets. However, there are instances when the data is what we call skewed. And there are two types of skewed data. The first is this. Notice the mode occurs farther to the right, and the data seems to have been stretched to the left. This is called a negatively skewed data set. Because the data has been stretched to the left of the mode. Likewise, we can have a positively skewed data set. Let me redraw that because it wasn't very good. So a positively skewed data set looks something like this, where the mode is farther to the left and the data looks like it's been stretched to the right. And this is a positively skewed data set. Now in any type of data set, we can have values that are really outside the range of most of the other values. And we call these outliers. For example, if I give you the data set that contains these discrete values, we can see that most of the values are pretty close to each other. Right, they're values that are between 1 and 10, or in this case 1 and 8. This guy right here in the middle, the 18, stands out to us, right? Because it's not close to any of the other data values. This 18 is called an outlier because it lies outside the normal range of values. Sometimes these values are accurately measured and they're just rare occurrences and they have to be included in our statistical analysis. However, other times we might recognize that the methods we use to measure these data values were incorrect, or there was an error and we can disregard them. But we have to take that on a case-by-case basis. Let's take a look at an example problem from the book. This is problem number 3 from exercise 8b from the text. In this problem, a randomly selected sample of shoppers was asked, how many times did you shop at a supermarket in the past week? And the column graph was generated from the data. We have 4 questions. How many shoppers gave data in the survey? How many of the shoppers shopped once or twice? What percentage of the shoppers shopped more than 4 times? And we're asked to describe the distribution of the data. In all cases, we need to refer to the column graph. So for problem A, we're asked how many shoppers gave data in the survey. And what we need to do here is find the number of shoppers that gave each of the responses, which in this case are 1, 2, 3, 4, 5, 6, 7. Well, we can see that 8 people shopped 1 time in the past week. We can see that 10 people shopped twice. 11 people shopped 3 times, 8 people shopped 4 times, 3 people shopped 5 and 6 times, and 1 person shopped every day of the week. So for problem A, we simply need to add these numbers together. And I apologize, this number right here is actually a 9, not an 8, and if we add those numbers together, we get 45 shoppers. The second question, how many of the shoppers shopped once or twice? Well, we simply need to add up these 2 columns, and that is 18. The third question is, what percentage of the shoppers shopped more than 4 times? Well, we first need to add up these 4 columns, which represents the shoppers who shopped 4 or more times. And when we do that, we see that we have 16 shoppers. But we have 16 out of 45, and we're being asked what percentage So we divide 16 by 45 and multiply by 100, and we get 15.6% of the shoppers. And the last question is to describe the distribution of the data set. So we can try to fit a bell curve to this data to help us see what's going on. And hopefully you can see that number 3, or the people who shop 3 times per week, is the mode because it occurs the most often. And we see that there are more data values on the right hand side, and that the right hand side is slightly stretched. So this data set would be positively skewed. It's also worth mentioning that there are no outliers in this data set.